Yes.
So I mean, it's great that you guys continue with your seminar. So actually, I was a little bit unclear about what the audience is going to be. So I have kind of multiple versions of the talk, and what I will do is maybe I will try to see how it goes, and then maybe I'll go to more or less details. So I cannot quite see everyone who is listening, but I don't know how to best manage.
If you
so
call it press on participants, you should be able to see it. We have more than 50 people.
Yeah, so, please speak up. I suggest that you speak up if you want to ask a question. So okay. So let me just start. So it's kind of something between a research seminar, I guess, and a colloquium. That's my understanding. And so I would like to kind of start maybe at a high level. So the field of quantum information science and technology is basically motivated by two kind of important observations. One is that information, its acquisition, storage, transmission, and processing is fundamentally done on a physical system. So it relies on the laws of physics. And the second point is that with all of the progress in conventional computing technology, the ultimate elements of sensors, processors, and transmitters will sooner or later will be of the quantum size. And motivated by that, already a couple of decades ago, people started asking, the question is, what if the size of the transistor becomes, say, a size of atom or a size of the electron? And whereas people initially thought that, this will be kind of a limitation, it turns out that it's actually an opportunity. So specifically that atoms, electrons, nuclei, photons, fundamental constituents of matter can actually acquire, store, and process information. And in fact, they are obeyed by the laws of quantum mechanics. And, as a result, you can actually start asking whether, these quantum systems can do tasks that classical systems have hard time accomplishing. And so that kind of motivated this broad field of quantum science and engineering, which is basically a quest, what I would call, for controlling quantum world. So specifically in this quest, what we are trying to do is isolate and control some quantum objects which are in some sense simple. Like these are, for example, two-state systems like nuclear spins or atoms or polarization of the photon. And then once we can really get full control of this, we can actually start wondering whether we can build more and more complex systems from them. And what we would like to do with these systems, we would like to explore new physics, and this will be the physics with basically engineered many-body systems. So in particular, one of the big tasks and big themes is how to create and probe new states of matter, in particular those featuring quantum entanglement. Then another question is whether one could explore applications of these techniques and applications like quantum processing, communication, and metrology. So this is now a big field, and I'm sure you've heard many talks about it. So basically, the kind of frontiers of this field now are twofold. On one hand, there is a question, can we really, build a truly large-scale controlled quantum system? So, in a number of laboratories, small, for example, quantum computers have been demonstrated. Can we scale them up? And the second question is, basically, what can we do with them? And actually, at the moment, in fact, there are not so many examples where this kind of controlled quantum systems can perform the actual useful tasks, either scientific or technologicals, that the classical computers cannot, or classical machines cannot accomplish. So that's what I call useful quantum advantage. And again, you've probably heard about quantum supremacy. So this is an example of the task which is, potentially unique for, where, quantum, machines can really have an advantage, but quantum supremacy, at least as of right now, is really not a useful task. So that's why I emphasize the word useful. And so basically, kind of motivated by that, there is, now kind of an active effort, around the globe towards, building and, thinking about what to do with quantum machines. And in a way, this is like a kind of a quantum rivalry. And, one could say, well, it's a kind of a competition between different labs, between different countries. But actually, I like to take kind of much more philosophical, maybe kind of Eastern, view of that. So in a way, this is really a competition between two competing trends of matter. So one is, controllability, where you really would like to isolate and maintain coherence and control it very precisely. And another one is scalability. And these two kind of trends are very, contradictory in not just in physics, but in many other kind of areas of activities around us. So for example, one example I often like to give is that if you, for example, take a bunch of smart people, like for example, mathematicians, and put them into a single organizations, and like, force them work together, then this kind of system will be very difficult to control. So, but in quantum physics is definitely a challenge, and the current frontier, see this kind of jokes across the Zoom are not going so well. So I don't know, hard to see. So the current frontier is really to kind of build machines which can do tasks beyond modern classical computers. And, that basically means that they should be able to control at least, 50 or maybe 100 or so of qubits. So motivated by this consideration, I will tell you about our work in this area using one specific system that involves basically using the individually controlled atom arrays. And I'll tell you how we can isolate single atoms and how we can build, systems in a controlled way from that. And then I will tell you a little bit about the kind of science which we can do with this system, and it will be a physics of quantum phase transition, in particular exploring quantum dynamics of the system. And hopefully I have a little bit of time to tell you about what we are doing now in our lab. So, so in our approach, we start with the atoms in the gas phase, and basically in a vacuum cell. And we use this so-called technique, so-called laser cooling techniques, which allow one to basically slow down their motion by shining laser light on these atoms. And then we use focused laser beams, these so-called optical tweezers, to grab these atoms. And the idea is we focus light so tightly that each of these, traps, each of these tweezers can hold at most one atom. But, when we try to kind of load them, we don't just try with one of these tweezers. We like to use many, like hundreds of these tweezers. And so what happens if we just, on one attempt, try to load them, what we find is that this loading is probabilistic, and it's because system has an entropy. And the way how we get rid of this entropy is by using the approach which is similar kind of to Maxwell demon, if you remember what it is. So what essentially we do is we take a picture of the atom, atoms, figure out which traps are full and which are empty, and then basically remove the empty traps, and then basically rearrange the full traps in any way we want. And so after that, we end up with arrays of atoms, typically separated by distances ranging from 1 micron to maybe tens of microns. So as such, this is a very regular kind of low entropy system, but these atoms don't talk to each other. They don't interact with each other. And then what we do to turn on these interactions and to engineer this interaction is we excite this atom into a state with principal quantum numbers. So remember the physics of hydrogen atom. Once you put the atom into this, very high state with high, principal number n, right? So this electron becomes basically only very loosely bound to the atomic core, and the atom size actually becomes very, very large. So the atoms in these Rydberg states, interact very, very strongly, and we make use of these interactions. So this work is actually a collaboration between several groups at Harvard and MIT within the Center for Ultra-Cold Atoms, and it's actually in particular collaboration of my group, the group of Markus Greiner at Harvard and Vladan Vuletic at MIT. So here is kind of the first generation of our experimental apparatus. So I emphasize that it's a first generation, and because I will talk towards the end about the second generation. So basically, the core of this apparatus is this device, which is called acousto-optic deflector. So it's basically the same type of device which is used in the supermarkets, to scan barcodes. And essentially what this device does, it takes as an input the one laser beam and the number of radio frequency tones. And then for each of these tones, the laser beam is deflected by a certain angle. And then basically by just collimating this beam and projecting it into the vacuum chamber, we create this array of tweezers. And then to basically, then what we do, we take the picture of atoms using, for example, a different objective, and then, figure out which tweezers are full and which are empty, and then remove the empty tweezers, basically by simply removing the RF tones driving these acousto-optic deflectors, and basically by shifting the frequency of RF tones, we can basically rearrange the remaining atoms. So this is actually the kind of the team, kind of a first generation of the team, which kind of built this setup, and actually several of them, Alex and Harry, the graduate students, and Ahmed is a postdoc, is actually still here, and Manuel is already a professor in Caltech, Hannes is a professor in Chicago, Sylvain is in Paris, and Julie actually is also still with us, So basically, this is a kind of the first, rearrangement images which we kind of created in our lab already several years ago. What you see here, we try to kind of fill 100 traps simultaneously, but in practice, there are only 60 or so atoms which are spread randomly. And then what we do is we just try to kind of move all of these atoms to the left, But we can, of course, also create different patterns, for example, clusters of 2, clusters of 10s, and these are all single shot images. What you see is that these are imperfect. For example, here is one atom missing, or here is one atom missing. And basically, but the probability that we create the desired arrangement is pretty good. And then one, of course, change the geometry with each repetition. So at this point, these are just one-dimensional system, and I'll tell you a little bit where we are kind of going to higher dimensions and larger arrays. But at this point, as I already mentioned, the atoms are separated by typically by a couple of microns, and they are non-interacting. To induce interactions between them, we excite them into the states with large principal quantum numbers. And what we make use of the fact is in the states when the atom size is large, they are actually interacting with each other very, very strongly. So for example, if you excite the atom into a state with n equals 100, the van der Waal interaction between such atoms is 14 orders of magnitude stronger than that between the ground state atoms. And at the same time, these Rydberg states are actually also very stable. They live typically, for like hundreds of microseconds. And so what we do is 14 orders of magnitude is a large number, so we can make good use of them. And one example how we can use of them involves the idea of the so-called Rydberg blockade. So what, the idea is the following. So suppose what you try to do is you try to basically excite the atoms directly from the ground state to the Rydberg state. So if the atoms are far away, then you can just excite them independently. They undergo independent radio oscillations. But when you start bringing atoms closer and closer, what happens in this case is that, eventually the interaction takes over. And what this interaction does, it actually shifts these doubly excited states, very rapidly away from resonance. So what it means is that if you keep the frequency of excitation of your, basically wavelength of your light the same, then eventually you will be able to excite, either one of the atoms that you are trying to promote to the Rydberg state, but not both of them, because doubly excited state is just shifted away from resonance. And it turns out that this is actually a very good mechanisms, very robust mechanism to create entangled states of these atoms, because this kind of mechanism, interaction mechanism, is insensitive to position, motion of the atoms. So it's actually kind of very, very reliable. And so basically, to kind of sum up, what we are going to do in what follows is experiments of this kind. So we'll first prepare a random arrangement of atoms, and then we will rearrange these atoms into desired configurations, for example, in this case, in the groups of 7. And then we will subject these atoms to sequences of laser pulses, some addressing these atoms simultaneously, some individually. But then at the end, we just make a projective measurement of the atom, and we measure the atom in a certain state, for example, ground or Rydberg state. And so what is, for example, shown here is that, you basically, the result of this measurement either finds that the atom is there or not. So it's either you have this dot, the atom, or not. So this is kind of will be a general approach. And so, like within the model of this type, we actually have now for the last few years explored a wide variety of different aspects of both quantum information science and many-body physics. So, for example, we implemented quantum gates of different variety. We have studied quantum phase transitions. We have studied quantum dynamics. We created large-scale entangled states. And you could say, well, they're all like kind of a little bit different tasks, but actually really not. So it's kind of different facets of the same phenomena. All of these directions are closely connected, and they basically rely on highly coherent, highly quantum mechanical, either analog or digital evolution. So what I'd like to do in the next maybe 20-30 minutes or so is just give you some sampling of some different results, different things which we explored. But maybe I should kind of pause here and ask if there are any questions, about at least. So that's at high level what we are doing basically, and I'm happy to answer.
Can I ask a question?
Yeah.
Just wondering, are there natural symmetries in this setup, or do you expect no symmetries in the Hamiltonian?
Well, these symmetries you build by hand, right? So you depending on how you arrange the atoms and how you excite them, you can either impose a symmetry or not. And you will see it in a second actually how.
Okay.
In fact, by changing, we can easily go. By changing parameters, we can easily sort of change the degree of symmetry, for example.
Okay, thank you.
Okay, so let me give, so that's kind of the real challenge here, because one does not see faces of people, and it's kind of hard to judge, whether one should go slower or faster. But so let me give you a little bit of some examples, and I'll just see how it goes with time. And so these examples will be from this area, involving quantum simulations. Is actually kind of where this, quantum wave, or quantum science as a field has started with the kind of paper by Feynman, where he pointed out that if you really would like to kind of simulate complex quantum systems, so it's actually much better to use quantum simulator, basically quantum mechanical simulator, where you can have some standard set of subsystems like qubits and programmable interactions. And this is simply because modeling quantum system exactly at least is very hard. So for example, for looking at dynamics, if you have n quantum bits, it requires solution to 2n quantum classical coupled equations. And therefore, like n equals 50 or so, it already becomes very challenging. So what we are going to do is basically, build a quantum simulator from these ideas which I just described. So let's kind of be a little bit more specific. So let's start now with the system where we arrange the atoms in a kind of a regular chain of equally distant atoms, and just ask what sort of Hamiltonians we can, realize and create in the lab. And so the kind of class of Hamiltonians is actually shown here. So let me just go, kind of step by step here. So we're looking at a chain of 1D chain of atoms, and let's assume there are only two states which we can access, ground state and Rydberg state. And basically N will, label a number of Rydberg atoms on each side. So in this Hamiltonian, there are a few terms. One is this kind of middle term, which kind of acts as a chemical potential. And this is basically a term which is proportional to a laser detuning, which can be either homogeneous for all atoms or can be individual. Now, let's assume that is, for simplicity, is homogeneous, and then basically, this term is as a chemical potential is just say whether atoms should be excited or not. So particularly if you look at the ground state, it's clear that for one sign of detuning, it would favor all atoms being in electronic ground state, and for other detuning, it will face all atoms being in the excited state. But clearly, if you excite all atoms, this is incompatible with this idea of blockade, which I described. So for example, if you just have nearest neighbor blockade, then what will happen is that you will not be able to excite every atom, but you will be able to excite every other atom. So this is the lowest energy state, which is accessible in this case. But actually, you can keep going. You could say, what if this blockade extends to a second nearest neighbor? Then, what will happen is that your state will break Z-free symmetry, and you can keep going. So all of these states, they're ordered states, they're kind of classical states, but they feature different, broken symmetry. And what we can do now is we can basically explore these states by just starting with all of our atoms in the ground state, and then with detuning, which is negative, and then just trying to change the sign of change the detuning across the going across the zero value, such that it changes the sign and such that it really enters into this state. And if you start with a system which is kind of not too big, let's say maybe 10 or so atoms, you can very kind of easily see that you indeed can create all of the states. So these are the this is a state with Z2 symmetry broken, up, down, up, down, up, down. So this is the state with Z3 symmetry broken, and this is a state of Z4 symmetry. So basically, in all of these cases, what you see is that you go across this point where a system is not so sure in which state to order, and this basically kind of like a toy version, if you want, of a phase transition. So here are a lot of fluctuations. And so what you already see here is that by changing, in this case, a spacing between atoms, you can basically change the blockade radius, and then what you could do, you could basically program the kind of symmetry that will be broken. But the real interesting, case is, of course, to go to much larger system size. And in 1D, we played with system sizes up to 60 or so atoms. So here is the image of 51 atom array with all atoms in the ground state. And if we now, for example, fix the blockade radius such that only nearest neighbors are blockaded, so we expect to create a Z2 phase, but actually, in practice, what happens is after the transition, you don't always have a perfectly ordered system. So here, the kind of system breaks into ordered domains, and in between these domains, this is basically this kind of defects, which are domain walls. So basically, this is like a classic picture of the phase transition in 1D. So you have these long ordered chains, and then domain wall in between them. And what you could do, you could, for example, ask a question, what's domain wall density? As you go across a phase transition, it changes smoothly. But you could also ask a question, what's the variance, or what is the distribution of domains? Actually, for example, here, the variance of these domain walls peaks close to zero detuning, and this peak is really a signature of a phase transition. So here, system just doesn't know on which side, whether to order or not, and basically that way we could really kind of identify where the phase transition occurs. Actually, in this case, it turns out that what the value we measured is very nicely in agreement with the prior theoretical work, which actually our colleague Subir Sajdiv and his collaborators have kind of predicted. They basically studied the model of this type. But so this is like looking at the system from a kind of thermodynamic perspective, but we could also look at it from microscopic perspective. We could, for example, ask what's the probability that each given state, occurs after many experimental runs. And what you see here is that already in this very early kind of results a few years ago, we found that, the most probable state actually is, this kind of ordered state where, they have a perfect, in this case, anti-ferromagnetic up-down order. And one could ask, then the question is, one could say, well, you could quantify the degree, to which you can really control the system is how likely you will create this ordered state. So initially, this ordered state, the probability was actually quite small, but actually by now you will see in a few slides, we were able to improve the system, but its probability is actually substantial, is much larger now than 10%. And you can also do other things. You can, for example, plot density correlation function, extract, for example, typical size of domains. And so basically all of this kind of very nice set of tools which allow us to have unique insights into phase transition, and especially in questions like quantum dynamics. Okay, so let me now give you just a couple of examples, and that's what we actually explored mostly for past 2 years or so. So one, this work actually has been done in close collaboration with several theoretical groups. One of them, Subir, and his student Ryan, who has actually done a lot of kind of important calculations and predictions. And another one is a Peter Zoller's group, and actually the two kind of our younger colleagues, Hannah Spickler and Sun Woon Choi has done kind of a lot of relevant work. And actually, I don't know whether I can, say that, but, Sun Woon will join us here in Cambridge at MIT very soon. I think it's kind of official by now. And Hannes is starting a position in Innsbruck. So, okay, so the first thing we explored is a situation where we go across phase transition kind of gently and slowly. And in this case, what one could study is something which is called quantum critical dynamics. And it's related to something called Kibble-Zurich mechanism. So what is that? Well, so if you have a kind of generic second order phase transition, what happens is that if you approach a critical point, then the correlation length would typically grow as a power law with some constant, which is with some power nu, which is actually known as a kind of universal exponent. And at the same time, at the phase transition, the gap between the ground and first excited state should also close in thermodynamic limit. And this is driven by something which is called Z, which is basically a dynamical critical exponent. So both of them are believed to be universal properties of phase transition. It doesn't matter what exact system you started with, and the microscopic details don't matter, but basically for a given class of phase transition, these two numbers are universal. And what Kibble-Zurich mechanism is basically kind of is a hypothesis which allows us to predict some non-equilibrium effects like creation of defects by using this universal critical exponent. The idea is basically the following. So if you go across phase transition with a finite speed, then eventually you will leave the ground state. You will start creating excitations. And what that means for correlation length is that initially, when you're far away from a phase transition, when you go slowly, the correlation length will keep growing. And then at that point where you broke this adiabaticity, the correlations will stop growing. And so basically the Kibble-Zurich essentially postulates is that the correlation length in the ordered state will be the same as at this so-called freeze out point. It's where this growth stopped. And basically what from there, for example, you can ask what will be the, finite length of the, correlated domains. And it actually turns out to scale the power law of this inverse speed with which you go across a phase transition, where this mu is the so-called Kibble-Zurich exponent. So, so this Kibble-Zurich mechanism is, of course, kind of known in many areas of physics. So it actually was initially formulated to describe the formation of early universe. But, like 15 or so years ago, there has been a couple of papers which basically pointed out that this should also be applicable to quantum systems, like quantum computers. But it's actually turned out to be quite challenging to observe that. And, and the reason is that basically the systems have to be isolated, and you have to go quite slowly to really explore this quantum critical region. So, for example, Wojciech Zurich, one of the people behind this Kibble-Zurich mechanism, has actually tried to do these experiments on a D-wave machine. But D-wave machine is basically not a fully quantum machine, if I may say. And there, of course, it didn't really work out. So he wrote this paper so that it's really a broadly applicable and easy to implement test how quantum is your hardware is in practice. And so we can easily try to do it, for example, looking at this Z2 transition. And what we do here is we can just go across the phase transition with different speed. And if we go fast, we have a lot of defects. If we go slow, we have few. And then we just look at this final number of the correlation length and just plot it as a function of the sweep rate. And we can easily fit it to the line. And actually from here, we can extract this mu, which is 0.5. So it turns out that 0.5 or 1/2 is exactly what the Ising model predicts, the quantum Ising model, and what our experiments in this case were in very good agreement with 1D Ising quantum phase transition. So, but of course, like once you have this tool, you'd like to do more things. And actually, in fact, what we did is we explored all of this phase diagram and measured not only this known Ising phase transition, but we also looked at transition as the free ordered state. In this case, it's actually described by something like chiral clock model, which has actually been a long-standing controversy. And we observed the exponents which are consistent with that. So I don't want to go into the details, but happy to answer any questions. And actually, we've even saw some plateau which is kind of transitioning to this Z4 state, which actually, in fact, people believe that it should not be direct transition, but anyway. So this kind of approach really allows us to really do kind of precision measurement of this quantum critical phenomena and understand quantum phase transition. So, but the other thing which we also have done is we've tried to go across the phase transitions quickly. And there one could really start a system on a path which is way away from equilibrium. And usually you would expect that such systems would thermalize. And this is actually one of the very first experiments that we have done. So we basically started with 5 atoms, for example, and then created this state up, down, up, down, up, down, going slowly. But then after that, after creating the state, we basically changed the laser detuning very quickly to just jump across the phase transition. And our original goal was to just see how the system thermalizes. And here are these trajectories of all 5 atoms in this case. So what you see is then eventually indeed some system thermalizes perhaps, but something non-trivial is going on. So I just will zoom at a couple of points. So for example, at this point, so initially this ordering disappeared, but then here this kind of complementary ordering reappeared. Up, down, up, initially it was up, down, up, down. Here is down, up, down, up, down, up. So you waited a little bit and then the original order disappears. So something funny is going on. And you could say, well, 5 atoms is just a small system with a finite size effect. But then we repeated this experiment for larger systems, for example, 9 atoms or 51 atoms, and we still see that, after this so-called quantum quench, after a rapid jump in the tuning, we observe that the system does not thermalize, but we see basically these oscillations of the order parameters. These oscillations have some frequency, which is kind of non-trivial, and the question is, where does it really, come from? So, and the point is that we are working with a system which is non-integrable, so in general should really, undergo thermalization. So you could say, well, wait a second, you have this blockade constraint. You cannot access the entire Hilbert space. It's true, but actually it turns out that our Hilbert space dimension still scales exponentially, and this, interestingly, it scales as a golden ratio to the power of n. So it's kind of, and it's not an accident, actually, it turns out. So, okay, so what is kind of going on? And so when we initially saw these things, it's already almost 3 years ago, we were very puzzled, and we started, doing numerical simulations. And then, for example, we used something which is called matrix product states as a way to kind of, write variational, wave function. And we saw that we can reproduce this effect. And actually, one kind of hint from early simulations which we saw about what's going on is by looking at the entanglement entropy. What we observed there is that the entanglement in the system grows, but it grows kind of non-monotonically. The system becomes entangled and then becomes disentangled, becomes entangled again and becomes disentangled again. And then basically as a result of this, oscillations in the entanglement, the overall trend, the overall entanglement entropy is growing very, very slowly. So, okay, so what's going on? So these robust oscillations are somehow connected to slow growth of entanglement, and most likely are due to this constraint dynamics due to blockade. And, they decay, but this decay is apparently due to long-range interactions, and that, I'm not going to talk about it in too much detail. So basically, we published these results, and, we were not really sure what's going on. And since when there has been a lot of theoretical work, and actually I will just, describe one sort of way to think about that, which I think is actually my favorite. And this is related to relating to this dynamics to something which is called quantum scars. So what are quantum scars? So these are the concepts from the single particle chaos. So if you start with the classical chaotic system like the billiard and ask a question, well, in this billiard, you can have some small number of these closed trajectories just from the symmetry considerations. So you could ask, well, what if you now quantize the system? Will there be any trace from these trajectories? And naively, you would say no, because uncertainty principle basically washes all of these things out. But actually, our colleague in the chemistry department, Rick Heller, already many years ago, pointed out that actually this these unstable trajectories in the classically chaotic systems can have non-trivial manifestations in quantum, in quantum description when you quantize. So basically, for example, you can have some eigenstates which very much resemble these classically chaotic periodic orbits, and this is what's called quantum scars. And there are now, this is actually, from what I understand, is a big field in this quantum chaos community. And the question, you can ask, well, what is the relationship between these quantum scars and what you guys are doing? So basically, these things which I've shown you, this kind of many-bodied, trajectories where you started in a certain state, and then this certain state thermalizes very slowly, could be thought as a kind of very special states, as this kind of quantum scar states, which are, basically embedded, throughout thermalizing many-body spectrum, but they can exhibit robust dynamics. And actually, it turns out that the best way to kind of think about these quantum scars, at least in my opinion, is in terms of these matrix product states, which I have mentioned. So these are basically the states where you where you construct a state in such a way that, you know, they have a limited degree of entanglement, and you can parameterize them with certain, you know, kind of new variables, and these new variables are like, you know, position and momentum. And in these kind of manifolds and kind of many body, you know, matrix product states, you can draw these trajectories, which are basically unstable trajectories. But, you know, those are the trajectories which correspond to this, to these oscillations. And actually, you know, we have done together with Van Wey, who is actually a postdoc here, we have done a lot of kind of analysis trying to basically really quantify and understand, you know, these many body scars in terms of this matrix product states. So, but there are many other things, you know, you could think about. So, for example, Daniel, you know, our high energy string theory colleague got very excited and pointed out that there are this, you know, very nice connection between basically potential connections of these many body scars with Kepler orbits in kind of dual quantum gravity description. So I think, you know, Daniel has not yet written a paper about it, but basically by now there are, and there is also people pointed out connections to lattice gauge theories, to things like string inversion. But basically by now this is actually quite popular subject. There is an archive paper almost every week kind of suggesting another kind of version or another explanation. And this actually is really an exciting field. So it's basically probing new physics far away from equilibrium. So let me just mention briefly one last kind of experiment that we have done with the 1D system. And this is related to this kind of idea of the, that I mentioned, to this, in particular, to this Google's experiment also in quantum supremacy, where the goal of these early, you know, experiments on large-scale systems are often to really benchmark, to understand how well these systems work. Can you maintain quantum coherence in a kind of large quantum state? And so one way to actually, you know, do it is to try to really create a large-scale entangled state. So I already mentioned entanglement a little bit before. It's intrinsic to things like dynamics. And what we can, you know, now try to do is create this kind of paradigmatic, you know, Schrödinger cat state, where, you know, system is in two states. One is like cat is alive, and another one, cat is dead. And one of those states is a so-called GG state, stands for Rydberg and Horn-Zeilinger, this name. And, you know, this is a state where, for example, all of the atoms are in a state 1 or qubits, and all of the atoms in a state 0 simultaneously, and there is a well-defined phase between these two states. So these kind of states are important for many quantum information concepts, but they're also known to be extremely fragile. So basically, if you just go and, you know, flip one qubit, you know, then you destroy the state completely. What's also actually nice, Wolf, is that these states are very easy to characterize. So generally, entanglement is very hard to characterize, but these GG states are special because basically you just need two elements of density matrix. You need basically two, you know, diagonal elements, you know, the probabilities to find a system in this state and this state. And then you need just a off-diagonal element, basically characterizing coherence between them. And if you have that, then you can immediately, you know, construct the overlap between the state you created in the lab and the target state. And it turns out if this overlap is larger than 50%, that's sufficient for n-particle entanglement. So the way how we can create this entanglement is by using exactly the same procedure which I described. So the only thing we need to start with even number of atoms. And the reason is that if, for example, go into this antiferromagnetic state, you here end up with state up, down, or down, up, down, up. You know, and if you can maintain the phase, and if you don't have any other admixture, then you can create states like this. So in practice, you always have other admixture. So for example, it turns out that the state where two edge atoms are excited are also very close in energy. And we need to kind of get rid of that. So in order to do it, we can basically locally apply effective magnetic field to penalize this state. So this is done by just shining tweezer light on these edge atoms and basically push this away. And then all we need to do is just now kind of make these transitions from the all atoms in the ground states to this up down states. We need to make this transition slowly and adiabatically. And when you have 4 atoms, it's actually relatively easy to do. So you just can do that and measure, and then you find that most of them are indeed these strings 1 0 1 0 0 1 0 1. This is by itself not quite enough to prove that you created GHG state. What you need to do, you also need to measure and control the phase between them. And the way how you can do it is shining this kind of, we call it staggered field, basically, shining light on every other atom, and that would change the phase between these 2 components. And afterwards, if you, for example, flip the bases and measure parity, you can get this fringe. So from these 2, you extract basically both diagonal and off-diagonal elements, and you can basically extract this overlap. You can, you can say immediately if your state is entangled or not. So for small system, it works very well. But if you go to, for example, 8 atoms, what you start seeing is already this kind of spaghetti of levels. And here, doing, this adiabatic transition becomes challenging. So this is a fundamental effect. There is no way around it, but one could at least try to kind of circumvent it somewhat. And so what we did here is we kind of teamed up with our European colleagues who have this optimal control solver, which basically allows you to find the kind of optimal path in the parameter space. And this path is not necessarily the slowest because of decoherence, but so for example, this is a trajectory where instead of kind of just, slowly changing the detuning, you kind of change the detuning across a resonance and do this kind of fancy changes in the Rabi frequency. And, they, allow to speed this up somewhat. And in fact, actually, effectively, even though it's an analog procedure, it allows you to effectively do like a deeper circuit on a quantum computer. So here is just, very quickly, the result that we have measured using 20 atom strings. So here, we apply this optimal control and just measure probability of all bit strings. And what you see, there are about 1 million states here, and what you see, there are 2 states which actually really stand out. So these are the states up, down, up, down, up, down, and down, up, down, up, down, up. So this blue is a raw measurement. This yellow is kind of inferred populations. We know that our detection, atom detection, is not 100% perfect, and small corrections, they actually affect the results. So but we can characterize them and infer the correct results. But see, this is basically a situation where all of our atoms in the entire array are correlated. And moreover, by shining this, staggered magnetic field, we can also imprint a phase and measure this phase. And from here, we can extract, for example, a fidelity, GHG fidelity as a function of n. And what you see is that even up to the arrays of 20 atoms, we can still, break this barrier of 0.5. So it means that it's a GHG state, certifiably GHG state, and it's actually the largest GHG state created to date. And what you can ask, where is it going? So I mean, like, this really is a way to benchmark our system. And in fact, we are improving, coherence and control. And the big kind of direction here is to try to understand dynamic robustness, distribution of entanglement. And in fact, such states, entangled states, can be used for things like metrology, for example, applications. Okay, so this is, kind of where we were maybe in the fall of last year. There are several directions where we would like to kind of, push this research forward. So I will maybe take 5 minutes to just give you a little bit of a sense, where is it going? And the big kind of goal here is to, scale the system up, improve coherence, improve controllability, and try to, use it for something, kind of interesting, both scientific, in a scientific sense, but perhaps also a little bit beyond. So let me just give you a brief kind of overview of what we have done since last fall. So basically, we have completely rebuilt at least a part of our system, and we have now a generation 2 system already working, where actually we create a trap using this device called special light modulator. It's basically a computer kind of generated hologram, which you can use to create basically an arbitrary two-dimensional pattern of laser beam. And if you basically project this in a vacuum cell vacuum chamber, you can create arrays containing thousands of extremely uniform traps. And then to sort atoms in these traps, we use not just one acoustoptic deflector, but two at an angle with each other, such that we can use rows and columns, atoms, kind of independently. So let me just show how it works. So this is an example where we have an array of 600 traps, and basically we're trying to load these atoms there in these traps. What you see is that in each kind of shot we have a random loading pattern. What we could say is, okay, so let's now try to use this initial pattern to deterministically fill, for example, 300 sites. And, so here is some attempt to do it. And of course, this is, you see, is not completely perfect, but it's pretty good. And once again, this is, a little bit slowed compared to real life, but, here is how we generate this array. So, again, there is a mistake once in a while. So each filling of each trap is maybe 99%. But once in a while we have things like this. It's basically perfect 300 atom array. And of course, this is not limited to the square atoms. We can program basically any geometry that you want. So in this case, for example, arbitrary field pattern, we can fill very, very nicely. So what do we want to do with that? One of the directions is now extend our one-dimensional many-body physics studies to 2 dimensions. And this is again a Hamiltonian, which we have already discussed a fair bit. So basically, if you now impose nearest neighbor blockade and try to excite the atoms basically into the Rydberg state, then you will be able to excite only every other one. So you will create this kind of checkerboard phase. So it's basically 2-dimensional, Ising, or if you want interferomagnetic phase. But of course, you can start playing, for example, with atom separation, with different kind of interaction, engineer interaction a little bit. And even in a square lattice, what Ryan, Van Wey, and Hannes, and Subir, have found is that it creates already a zoo of different phases, And so what we have done now, we started just kind of getting a glimpse, into the zoo. But actually, one of the things that even this transition into this checkerboard, the Ising transition, apparently, according to Subir, which usually knows what he's talking about, has never been observed. So how can we do it? Well, we just can follow the same recipe as before. We create the pattern and, for example, square array, go into scan eddy tuning and try to see what happens. And what you see is that we're actually entering into this kind of checkerboard phase. Not perfect. Again, there are some mistakes, or here are a couple of mistakes, but it's pretty good. And what we can do, we can analyze it. For example, looking at correlation function, we can extract correlation length. But we can also immediately deploy, for example, this Kibble-Zurich approach, where we just go slowly, with variable speed across the phase transition, and from here we can immediately extract this scaling exponent. So in this case, there are calculations. You can map this, kind of model into a classical models in 3D, and can extract the scaling exponent. But apparently, this has never been observed in any system. But we can also, and actually we're very excited about kind of, extending this work to all sorts of exotic phases, also topological phases. But we are also quite interested in the other set of questions, and these are related to applications to optimization problem. And so here is a little bit, of mathematics kind of, for you guys. So there is a problem which is actually very well known and P-complete problem called maximum independent set, which is actually defined on a graph where you have some vertices and you have some links which are connected, we call edges, which connect with them. And the independent set is subset of these vertices, such that, basically, this, guy, for example, this red guy is not connected to any other red guy. So you color, and the goal of the maximum independent set is to basically find the independent set which will have maximal number of these colored vertices. So in other words, so I'd like to color as many of these vertices red as possible, but you cannot color the connected one. So what's shown here is one example of MIS on the so-called unit disk graph, where vertices are connected if they are within given distance. And so basically it defines this kind of complex network. So, when, everyone is allowed to fly again, if you open the back cover of airline magazine, this is the kind of picture that you see. And actually, it tells us something. So in fact, it turns out that, this MIS in particular, unit disk MIS, has many real world applications, in particular in design of network, but also in machine learning. And actually, it turns out that this, finding this, my MIS, even for this unit disk graph, is very hard. It's actually an example of NP-complete problem. So those of you who still followed my talk and, did not get completely lost can immediately realize the connection that this problem has with Rydberg blockade. So when we try to excite atoms under the conditions of Rydberg blockade, we are trying to excite as many atoms as possible, excited atoms like colored, on this on this graph, but we cannot excite them within the blockade radius. And this is what determines this unit disk. So basically what we would like to do is we would like to utilize this natural mapping to really try to see how the quantum machines can help solving this kind of problems. And so this work is based, of course, is on many other prior ideas involving both adiabatic evolution and annealing and something which is called QoA. And so what we would like to do, we would like to implement these algorithms here very efficiently by using this kind of co-design, by utilizing these natural connections. So let me just, I'm about to finish, let me just show how, like, it's the first times we are kind of trying to test, for solutions of this problem. So for example, let's consider, this arrangement of atoms. This is a subset kind of a square lattice with edges connecting, for example, nearest neighbors and next nearest neighbors. They are adjusted by using, for example, the blockade radius. And, then this, this problem still can be solved. So this is a maximum independent set. But, for example, for this MIS with this, 0.8 kind of feeling, it actually turns out that, if you start scaling the system, then the problem becomes hard. And it's actually believed that this exact solution is believed to scale exponentially. So what we can do to kind of test, look for solutions in our system is just implement the arrangement where we put the atoms exactly where these points are and set a blockade radius such that both nearest neighbor and nearest neighbor excitations are prohibited. So that's how this mapping works. And then what we do, we, for example, somehow try to look for the ground state of this model, either variationally or adiabatically. And basically, at this point, we just want to see, what kind of algorithms perform well and what not. And so here is, first tests. This is involving, this kind of quasi-adiabatic sweeps, similar to, but not quite as optimized as our GAG generation. And so in this case, we, try to enter the ground state. So, I mean, we find some independent sets, they're maybe not maximum, and we can, for example, try to, test how this algorithm works on different input sizes. So these are the size with 39 vertices. At this point, you can still simulate quantum mechanically the evolution, I believe. But go to 80 vortices will be actually very hard to simulate quantum. It's impossible, I would say. And here's 180. So what you see is, in this case, these sweeping parameters were kind of kept the same. And what you see is that, not surprisingly, the probability to find MIS, which is actually shown by this black line, is decreases exponentially. But then again, we did not yet deploy all of the machinery which we have. For example, like trying to optimize this path, try to do maybe closed loop optimization is the kind of stuff we would like to explore. So just one slide I added since I see that Eddie is here. So we've also started trying the QAA. And QAA is kind of is a new, relatively new class of variational algorithms, where you basically try to explore paths which are not necessarily limited to the adiabatic paths. And it turns out that in our case, we can implement this QA very efficiently by just applying the kind of Rydberg blockade Hamiltonian with different parameters. For example, by changing the phase of the laser. So here is this is the first step of QA where we just apply this, one layer, if you want, and just change the duration of this kind of application by playing with by changing the basically the time on with which you apply the laser, and you can find some distribution of the outcomes. But then you go to the next layer and you apply, for example, this Hamiltonian, the laser with a different phase, and actually we find, for example, that for p equals 2, we see some improvement. And actually, this is kind of not, it's a very much toy example with small number of atoms, and very shallow depth, and it's not as good as this quasi-adiabatic sweep, but actually it's already kind of starting to get us into the interesting territory. And once again, now we're working on things like, circuit optimization, closed loop, and, quantum classical benchmarking. So I think I hope I convinced you that it's actually an exciting direction where, the many body physics, interesting computational problems, entanglement, and especially experimental quantum science really converge. I think I used up my time, so I'd like to thank you for your attention. And actually, I'd like to also thank the group, the people whose blood and sweat resulted in this work. And here is, something, for you to enjoy, Thank you very much.
Thank you very much. Anybody, if you have a question, please feel free to unmute yourself and go ahead.
Hi, Misha.
Yeah.
Thank you very much for a very interesting talk. I had a short question about the Rydberg Hamiltonian.
Yeah.
So there's 3 terms, right? So the chemical potential, the PXP, and the attraction. I was wondering how hard or easy is it to add additional terms to the Hamiltonian?
So it depends on what kind, right? So
for example, correlated, like flipping 2 spins at the same time, something like that. So
it is possible. So, that's actually an interesting question. So basically the question is, can you engineer some kind of multi-body interaction, for example?
Yeah.
And it is actually possible. So, so there are 2 ways to do it. One of them is just by playing, for example, with different excitation schemes. So what you could do, you could invoke, so you can, for example, involve different types of Rydberg states, which would have very different kind of, for example, blockade range. And then, by, for example, just playing essentially with multi-level structure of atoms, you can engineer effectively a multi-body interaction. And one way of doing it is just kind of directly engineering the interaction. Another way is through the sequence of laser pulses. It's a little bit like kind of a trotterized way, but it can be very, very efficient. And We've done a little bit of that. For example, we've implemented this, like a Toffoli gates, just, directly without breaking them down into two-body gates. So that goes along this direction.
Very interesting. Thank you.
Hello, this is Bert Halpern. I have a question.
Yes, hi, Bert.
Hello?
Yes, I'm listening. Yes.
Yeah, so I thought you were saying when you were talking about the Kibble-Zurich mechanism in one dimension that you were getting, you were quoting, if I got it correctly, that the correlation exponent nu and z were equal to a half, whereas the mean field is a third. Did I hear that right?
No, so it's basically...
That's confused me because I would have thought that mean field would be a half, and yeah.
So it's basically...
Maybe I got it wrong.
Yeah, so so basically, so what you need is kind of z and mu.
Right.
Right? And for this kind of quantum phase transition,
okay, yeah, all right.
It's actually z and mu is 1.
Oh, okay, right, okay.
Right? It gives mu 1/2, right?
U is a half. Okay, I just misread it. Thank you.
Yes. And this mean field, okay, one has to be kind of a little bit careful what you define as a mean field, but I think conventionally people would quote like one third. For example, for system which is coupled to like thermal bath, this is, that's what one would. So. Don't know if I aimed it correctly for mathematician, but I think there are a lot of physicists also in the audience. I figured.
Hello, can I also ask a question? I'm Dilek. Considering these phase transitions, so I understand kind of what they mean, I suppose, but when we actually have phase transition depending on temperature, can we actually drive them into transition by giving some energy, like heat or?
So there are, in nature, there are basically two different types, several different types of phase transitions, but and kind of most of them which are known to us, for example, like freezing of the water, right? This is a transition driven by thermal fluctuations, right? So there, indeed, you kind of change the temperature, for example, and for the Kibble-Zurich mechanism, all initial kind of thoughts were you basically change some parameter like temperature or kind of pressure or something like that. But actually, the kind of phase transitions which I discussed here are a little bit different. So they are the so-called quantum phase transitions. So they occur actually at 0 temperature. So there is no thermal. So in our case, the system is really isolated from the environment. And so we work very hard to prepare it at absolute kind of 0 temperature. And I think we can do it with to very, very high degree, And basically these transitions occur when you change, certain parameter. So for example, like, you change laser, frequency or detuning. such that you basically kind of start favoring some quantum fluctuations. So these quantum phase transitions, so for example, like the one which I, maybe the nicest way is to kind of, show here, right? So you basically, you kind of try to coherently excite that to flip these spins. So these are all individual spins, right? Which you try to, with the laser, flip, right? And, basically there is no temperature in this problem. So and these transitions are basically given by what people say quantum fluctuations. So as such, they're kind of different. And in order to study, to study them, we really have this very highly isolated systems. So that's what's special.
And the fluctuation, so you actually basically look at the fluctuation dynamics of the system then, is it?
So we'll look at fluctuation. Yeah, so we can do different things, but we can look at fluctuations by essentially taking these pictures, right? So basically what you do, for example, here, in this example, you go across this phase transition, and if you would have basically perfect ground state, you would have everything. Let me just show. So you would have complete order across the entire system, right? You would have states like this. But in practice, it's still not perfectly ordered. And what you do, you just take the pictures and you directly in your image see it. So here is a domain wall, here is a fluctuation, So that's what we do, right?
Okay. Another thing, I'm a little bit confused. Are we talking about okay, I understand that they are not maybe single particles, but are we talking about a fluctuation of a certain state, or the fluctuation in the global system?
We talk, basically with, so these are the so there, if you want, it's like, so it's a quantum system, right? And so kind of the way how to think about that is that, let's say, in a quantum state, you would, generally have, let's say a fluctuation like flipped spin on, in this case, domain wall,
Okay. Yeah.
which is encoded in a wave function. But of course, then you make a measurement, right? And you make a projective measurement, you find where it is, right? And so it's like, it's like in the quantum system, right? It's a fundamentally probabilistic description, right? And basically, but what we can do, we can, for example, find the complete probability distribution, which describes this fluctuation and stuff like that. Does it make sense or not quite?
Yes, now it's way more clear, and I can imagine the.
Yeah. And because we have an access to basically both microscopic and microscopic degrees of freedom, we can really study these things, right?
Yes, thank you very much.
Yeah.
I have a quick question. Have you guys looked at or done anything on non-ordered arrays, or do you have any sort of eyes on that?
Disordered arrays or ordered arrays?
Disordered arrays.
Well, we have done a little bit, but not not whole lot. So maybe the closest which so of course, and it's of course a very interesting direction. So in particular, in 2 dimensions, when you start playing with this kind of systems which are frustrated, so that's where you can expect, some interesting things to come out. And so, for example, this very nice phase diagram that Ryan has kind of generated. So in this case, it's kind of interesting because array is still ordered, but because of long-range interaction, there is basically, sorry, let me just see if I can. So there is this kind of frustration. There is a natural frustration in the system. So even in a square lattice, it turns out you have basically a competition between these different kind of orders. And that's what results in this kind of fancy phase diagram. So we have actually started already exploring that, and we see some evidence of some of these phases, and some of them are very, very interesting. So for example, this this little phase, which here almost non-existent, called striated phase, which has basically kind of underlying crystal of Rydberg atoms and then fluctuations. The atoms, basically, atoms are fluctuating in between. So this is already a little bit like, I guess it's a tip of the iceberg, but I mean, these are definitely, I think this kind of looking at these things at frustrated or disordered arrays is very, very interesting. And of course, for solving, for example, MIS problem, that's where we work with disordered systems. I mean, that's how we encode the problems, right? That's another example, right?
Thank you.
So Misha, can I ask a question?
Yes, of course.
So regarding this frustration that you're mentioning that has origin because of this long-range interaction, so does it show some effect of a spin glass or some glassy phases, or we cannot?
Okay, so I don't know. It's maybe if Ryan is online or Subir, they should answer. So, I think this frustration which we are talking about here on this slide, maybe not. I mean, certainly this when you start talking about something like MIS, right? So there are definitely the glassy physics. I mean, so this type of stuff, right? Basically, there is absolutely should be a glassy physics, and that's why these problems are hard, right?
Right.
Right. So, but in this example here, I don't know whether I would actually call it a glassy physics. I think it's more like competition between different orders. Really, but maybe Subir or Ryan or One Way, maybe they could answer better.
Yeah, but like maybe my question would be also what kind of like parameter regimes would just like push us to some more like glassy phases.
Yeah, I think it will not be too hard to create. I mean, once you start, for example, in arrays which are not ordered, almost certainly will be glassy physics, right? And, I mean, that I think it's very much related to this MIS.
Creation.
And it is actually the fact. I think the fact that this MIS isn't P-complete is basically, I think, at least in my naive view, is related to the physics.
To the ground state of the,
yes, absolutely.
Yeah.
Because you have a lot of this local minima, which you just end up kind of. Okay.
Yeah.
So.
Well, thank you very much, Michelle. It's a great talk.
Yeah, thank you, Sergey. Thank you for organizing. Thank you for pushing me to do that.
Thank you for agreeing.
Yeah, thank you. Thank you so much. All right.
Okay, goodbye.
Yeah, yes, stay safe. Yes.
Okay.
Bye.